chemical engineering through e-learning. Morning students. Today I am going to solve a problem. This problem comes under the category of energy balance in a closed system. The problem is air initially at a pressure of 480 kilopascal and a temperature of 463 degree Kelvin is expanded adiabatically to a pressure of 94 kilopascal. It is then heated at constant volume until it attains its original temperature when the pressure is found to be 150 kilopascal. State the type of compression necessary to bring the system back to its original pressure and volume. Find the index of adiabatic expansion and the work done per kg of air. That's all.
Okay, students, let us start to solve the problem. A simple PV diagram is enough to explain the process. See, this is the y-axis, this is x-axis. In x-axis volume, in y-axis pressure. This is state 1. State 1. State 1 to state 2 seems to be like this. State 2. Okay. This is the adiabatic expansion process. And state 3. State 2, state 3. Volume is constant. This is constant volume process. Again, from state 3 to state 1, the system attains its original state. Okay. In state 1, P1 is equal to 480 kilopascal and temperature 1 is equal to 463 degree Kelvin. V1, there is no information regarding the volume of gas, leave it as such. Coming to state 2, P2 is 94 kilopascal and T2, there is no information regarding temperature at state 2, but temperature gets drastically decreased. Okay. And what about volume at state 2? V2. Again, there is no information regarding volume, but important thing is volume is increased from V1 to V2. Volume is increased. Okay. Coming to the point of state 3. In state 3, again it reaches to its original temperature. The pressure at state 3 is equal to 150 kilopascal and temperature is 463 degree Kelvin and volume V3. Again there is no information of volume at state 3, but thing is state 2 and state 3 are constant volume process. Hence V3 is equal to V2. With this information, let us start to solve the problem. Before to solve the problem, what about the type of process? Process 1 to 2. It is a reversible adiabatic expansion. Reversible adiabatic expansion. Okay. And process 2 to 3 is constant volume process. Or you can say that isochoric process. Isochoric or isovolumetric process. Okay. Process 3 to 1. Temperature is constant. It's called as constant temperature process, or you can precisely say that reversible isothermal compression. So this is your first question. State the type of compression from process 3 to 1. Process 3 to 1 is the reversible isothermal compression process. Okay. solve the problem step one by one. Process 3 to 1. Process 3 to 1. See, in this process, temperature is constant. T3 is equal to T1. For an ideal gas, P1 V1 by T1 is equal to P3 V3 by T3. Since T1 and T3 are constant or equal, this volume is initial, this is final. So V3 by V1 is equal to V3 by V1 is equal to P1 by P3. This is a pressure volume relationship between pressure and volume for the process 3 to 1. That means reversible isothermal compression. V3 by V1 is equal to P1. We know the value. That means 480 kilopascal, and P3, this is 150 kilopascal. 150 kilopascal. We no need to go for calculation. Just we establish the relationship. Again, process 2 to 3. Process 2 to 3 is equal to constant volume process. Constant volume process. Hence, V2 is equal to V3. Therefore, I wish to write like this. Instead of V3 by V1, I can write V2 by V1. V2 by V1 is equal to 480 divided by 150. Okay, wow. Next. Process 1 to 2. Process 1 to 2 is the adiabatic expansion. It is an adiabatic process. Adiabatic process. For an adiabatic process, the general PV relation is PV power gamma is equal to constant. PV power gamma is equal to constant. In this relation, I can write like this. P1 V1 power gamma is equal to P2 V2 power gamma. Hence, P1 by P2 is equal to V2 by V1 power gamma. Am I right? P1 by P2 is equal to V2 by V1 power gamma. On taking natural logarithm on both sides, gamma is equal to R ln P1 by P2 is equal to gamma into ln V2 by V1. Therefore, gamma, index of adiabatic expansion, gamma is equal to ln P1 by P2 divided by ln V2 by V1. Gamma is equal to ln P2 by P1 by P2. It is 480 divided by P2 is 94. P2 is equal to 94 divided by ln V2 by V1. Ln V2 by V1 is equal to 480 divided by 150. 480 divided by 150. Hence, gamma is equal to 1.4081. This is the index of adiabatic expansion process. Next, we will try to solve the. Let us find out the work done in each process. Process 1 to 2. It is a reversible adiabatic expansion process. Reversible adiabatic expansion process. Reversible adiabatic expansion process. Reversible adiabatic expansion process. Okay, since it is an adiabatic process, the first law of thermodynamics is change in energy is equal to dq minus dw. Since it is an adiabatic process, there is no exchange of heat. So du is equal to minus dw, or you can write like this: dw is equal to minus du. Change in energy in terms of heat capacity. So that is called as Cv into dt. So to minus Cv T2 minus T1. You can write Cv into T1 minus T2. These concepts are already well established during the theoretical classes. Even though I am trying to bring some remembrance. Okay, this equation can be written like this: Cv divided by R into R. There is no changes. Multiplication divided by R into T1 minus T2. See, this is Cv by R is equal to 1 by gamma minus 1. 1 by gamma minus 1. Hence I am going to write like this: R into T1 minus T2 divided by gamma minus 1. Okay, wow. So work done in a adiabatic process. Work done in a adiabatic process is equal to adiabatic expansion process R T1 T2. R is known 8.314 kilojoules per kmol degree Kelvin. Temperature T1 is given, but T2 is not given. Or the gamma value and index of adiabatic expansion is known. Only parameter is T2. T2 is unknown. For T2, the temperature and pressure relationship for an adiabatic process, the temperature and pressure relationship T2 by T1 is equal to P2 by P1 power gamma minus 1 divided by gamma. This is already established for an adiabatic process. You no need to spend time unnecessarily. So T2 by T1 is equal to P2 is given. P2 pressure at state 2, that's I think 94, pressure 1 and 480, gamma value 1.4081 minus 1 divided by 1. So T2 is equal to T1 value, T1 into this information, that is T1 is nothing but 463 into 94 divided by 480 to the power of 1 minus, that means 0.4081 divided by 1.4081, here 1.4081. So T2 is equal to 290.6 degree Kelvin, 290.6 degree Kelvin. Temperature is 290.6 degree Kelvin. Now substitute the T2 values in this equation. Substitute this. That means work done by the system. W1 2 process 1 2 is R 8.314 kilojoules per kmol degree Kelvin into temperature. That means T2 value, T1 value is equal to 463 minus 290.6 degree Kelvin. Okay, wow. Divided by this is temperature degree Kelvin, Kelvin gets cancelled, divided by gamma minus 1, gamma 1.4081 minus 1. The answer is 3.5 kilojoules per kmol. W1 to 2. Work done by the system. Answer is plus, hence it is work done by the system. Next, process 2 to 3. Process 2 to 3. It is a constant volume process. Constant volume process. Hence there is no work done by the system. That is W2 to 3 is equal to 0. Okay, wow. Next, process 3 to 1. Process 3 to 1. This is the reversible isothermal compression process. Reversible isothermal compression process. Reversible isothermal compression process. Since temperature is constant, according to first law of thermodynamics, du is equal to dq minus dw. There is no changes in temperature. If changes in temperature is there will be changes in entalpy. Since it is a constant temperature process, del U is equal to 0. So dq is equal to dw. dq is equal to dw. Clear? Okay? dq is equal to dw. And dw is equal to P into dV. dw is equal to P into dV. For an ideal gas, P is equal to nRT. For 1 moles of an ideal gas, P is equal to RT. For P, it is RT by V. P is equal to RT. For P is equal to RT by V, because this is the changes in differentiation of volume. I need 1 by volume term. So R into P into 1 by V into dV. So dW. So W is equal to R into T into ln. See, state 3 to 1, initial to final. So initial to final, V1 by V3. Okay, wow. V1 by V3. RT ln V1 by V3 W. For an ideal gas, V1 by P1 is equal to P2 V2 by P3 process 3 P3 V3 by P3. Temperature is constant, hence P1 V1 is equal to P3 V3. Now I am need of V1 by V3. V1 by V3, that is equal to P3 by P1. P3 by P1. So work done in a isothermal, reversible isothermal compression 3 to 1 is equal to R into T into ln. Instead of V1 by V3, I am going to write like this: P3 by P1. P3 by P1. R is equal to 8.314 kilojoules per kmol degree Kelvin, and temperature is constant, that means 463 degree Kelvin into ln P3 value. What is the P3 value? That means 150 divided by Q1 value 480. This is the answer. So W 321 is equal to 4477.4 kilojoules per kmol. The answer is negative. This is work done on the system. So in the first case, process 1 to 2 is 3583.5. This is the positive quantity work done by the system. In second process 2 to 3 constant volume process, there is no work done by the system. And process 3 to 1, it is a reversible isothermal compression process, and amount of work done on the system is a negative. So net work done, W is equal to W1 to 2 plus W2 to 3 plus W3 to 1. Therefore W1 to 2 3583.5 plus 0 minus 4477.4. That is equal to, the answer is what's the answer? The answer is minus 894.2 kilojoules per kmol. Minus 894.2 kilojoules per kmol. The question is net work done per kg of air. What is the molecular weight of air? So total work is W is equal to 894.2 kilojoules per kmol. That is negative quantity. The question is amount of work done per kg of air. The molecular weight of air is equal to 28.89 kilojoules, kg per kg mole. So W is equal to minus 894.2 divided by 28.89. This is kilojoules per kmol. This is kg per kmol. So kmol gets cancelled. The answer is kilojoules per kg of air. What is the answer? Minus 30.83 kilojoules per kg. Minus sign indicates this much quantity of work done on the system. 30.83 kilojoules of work done on the system per kg of air. This is the answer. Thank you.